this is heat equation video. So this is the second of the 3 basic partial differential equations. We had Laplace's equation. That was, time was not there. Now time comes into the heat equation. We have a time derivative and 2 matching with 2 space derivatives. So I have my function, my solution depends on t and on x. And I hope I can separate those 2 parts. This is exactly like the way we solved ordinary systems of differential equations. We pulled out an e to the lambda t, where lambda was the eigenvalue, and then we had the eigenvector. Here, it's an eigenfunction because it depends on x. We didn't have x before, but now we have partial differential equations. X is also a coordinate here, and so I look for solutions like that. And just as always, I substitute that into the differential equation and to discover what determines s of x. Okay, the time derivative brings down a lambda. The space derivative has two space derivatives. So that's what I get when I substitute e to the lambda t s, eigenvalue times eigenfunction, into the equation. And always, I cancel e to the lambda t, that's the beauty of it, and I have an eigenvalue equation. Or I'm looking again for a function. So the second derivative of my function is lambda, some number, times my function. Okay, what I'm looking for functions, s, they'll be sine functions. S will be, s of x will be the sine of k pi x. The sine of x, the sine of something times x. What's the eigenvalue? Take 2 derivatives of this. I get back sine k pi x, which is, so that's great. It's an eigenfunction. And out comes the eigenvalue. Lambda is, well, when I take 2 derivatives, k pi comes out twice with a minus sign. So it's minus k squared pi squared. So I have found a bunch of eigenvectors, eigenfunctions, and the eigenvalues. So now, so this was a simple pair, but now general solution. The general solution, u of tx, will be, if I know several solutions and I have a linear equation, I just take combinations. That's always our way. Take combinations of those basic solutions. So I'll have a sum, k going from 1 to infinity. In partial differential equations, I need a big sum here of some coefficients. Let me call them bk times this solution, e to the lambda. What was lambda? Minus k squared pi squared t times s number k. I should have given this eigenfunction its number, k. So there's the this is my family of eigenfunctions and eigenvalues, and then this is the combination of these solutions. There's the general solution, and for sk, I should have written in sine k pi x. So that's the dependence on t. Let's have a look at this. So the dependence on t is fast decay. And if as k gets larger, later terms in this sum, the decay is really fast. So the term that decays most slowly, k equal 1, there'll be a b1 and e to the minus pi squared t. That's decaying already pretty fast. When I'm talking about decay, what's happening here? I have a bar, a material bar. The ends of the bar are kept at temperature 0. They're frozen. And heat is in the bar. Heat is flowing around in the bar. And where is it going? It's flowing out the ends. The bar is approaching freezing. The ends are kept at freezing, and the inside of the bar, whatever heat is there at the beginning, is going to flow out the ends. So you see that I have these sine functions. When x is 0, the sine is 0, so that's frozen at one end. When x is 1, I have the sine of k pi, which is again 0, so it's frozen at the other end. So I'm freezing it at both ends. The temperature is escaping out of the center. So the solution, so let me graph the solution. So maybe I start with, here's my bar from 0 to 1, and I'm keeping it frozen, F for frozen at that end. Maybe I start off with a warm bar. So u at 0 on x, I'll say be 1. This way is x. So I have an ordinary heated bar, and I put it in the freezer. So I insulate the sides, so it's the heat is escaping out the two ends. Out the end x equals 0, and out the end x equals 1. And the solution will be this. Let me remember what the general solution looked like, and I have to find these numbers. Okay, so, and those numbers, of course, the numbers are always found by matching the initial conditions. This is the initial picture. Okay, so I have to match that by, so this is t equals 0. I have to match the sum of bk. This is k going from 1 to infinity. When t is 0, this is 1, and I just have the sk, the sine of k pi x. That has to match the 1. And when from that I find the bk's, and then the final solution, t greater than 0, is uses those bk's. And we're again faced with a Fourier series problem. Anytime I have to find these coefficients, this is a Fourier sine series. I have only sines, not cosines here. And I'm finding the coefficients so that this will match 1, the initial condition. And then for t greater than 0, the solution u will be, as we said, a sum of these bk's, which come from the initial conditions, come from this, Fourier coefficients. We still have to do that video on Fourier series to know what these numbers will come out to be, times the e to the minus k squared pi squared t times the sine of k pi x. You may think, well, that's a pretty messy solution because it's an infinite sum, but it's not bad for partial differential equations. We have numbers, we have something depending on time and decaying rapidly, and something depending on x. So that at time 1, if I drew a picture, suppose, so there, the temperature starts out through the whole bar at 1, but with this kind of time decay, a little later in time, the temperature is going to be something like that. It'll be way down at the ends, pretty low in the middle. And so at some time t, the temperature will look like that. And then soon after that, the temperature will go down to here. And the steady state, of course, is the whole thing is at temperature 0. So that's what solutions to the heat equation look like. And this is the step of finding which I didn't take, this is the Fourier series step of finding the coefficients in our infinite series of solutions. Once again, we have infinitely many solutions. We're talking about a partial differential equation. We have a whole function to match, so we need all of those. And Fourier series is the is tells us how to do that matching, how to find these BKs. So that's a separate and important question for